My colleagues Ayush Patnaik, Anshul Tayal, Susan Thomas, and I have this new paper on the clouds that interfere with nightlights data. Nightlights is a remarkable moment in economic measurement. We have satellites that look from the sky and don't rely on local institutions for economic measurement. And this is just absolutely wonderful, particularly in developing countries where economic measurement is so difficult. The first wave of this work had annual images for 1992 to 2013, and then from April 2012 onwards, we've got this new VIIRS sensor where a pixel is a half kilometer by half kilometer, and the data is observed every month. And this is a whole new world of economic measurement. In this paper, we do two things. We show that when there are cloudy months, there is a downward bias in the VIIRS radiance data. And we offer a partial solution for this problem. We offer a bias correction algorithm that partly solves the problem. What is the data that we're using? We're using the standard NASA, NOAA, VIIRS nightlights data. For the square that contains India, it is 16.7 million pixels. So there is a 72-month time series with 2 columns for each of these pixels. In addition, we use some other cities. So we've got Dubai and Singapore and Johannesburg. So we do use some other elements of this data as well. And for the ground truth in India, we use the CMIE CPHS household survey data, which gives us aggregate income in each of 96 homogeneous regions of the country for every month. Just to explain what the nighttime lights data is, it's a monthly time series where for every month there are two numbers. One number is the radiance that is observed in that month, but that is the average of the radiance value seen on the days that are considered to be cloud-free. So NASA, NOAA count the number of cloud-free images in a month, and they report the sample mean of the radiance seen on those cloud-free days. And their algorithms are reasonably stringent. As an example, consider December 2019. December is a reasonably bright month in India. But if you look across all those 16.7 million pixels, the 25th percentile value for India was just 10 days of cloud-free images for December 2019. So it's not as if NASA and NOAA are recklessly letting a lot of images be used for this averaging. They're trying to find cloud-free images. So let's get started with this data. The first stage that everybody has to do is called conventional cleaning. There are three well-known problems in this field. The first is, what do you do in a month where there are no cloud-free images? The second is that there are certain pixels in which there is lightning or there is a gas flare, and those are just outliers. And the third is there is a problem of background noise. Even in pixels which are forest or fields, there is background noise that is coming through. The World Bank has been an important part of research in this field. They have released a data set for 640 districts of India where they have done this conventional cleaning. And this data set is very widely used by researchers. They have been extremely generous in releasing this data widely. For example, we had no difficulty in accessing their data. We have made small methodological improvements on the state-of-the-art methods in the literature on conventional cleaning, and we have built and released the first open source implementation of conventional cleaning. In conventional cleaning, one element that is done is to define something that is called lit pixels. Many pixels are just dark. There are pixels which are desert and forest and fields, and there's nothing going on there. And they do pick up background noise. They add up background noise. So it's important to just remove them from the reasoning. And so when we start from 16.7 million pixels for India, we end up with 8.6 million pixels that we consider lit pixels. So that's going to be the main data set that we work with. Here's an example. This is a pixel in Bombay. This is 1 pixel in Bandra West. The red line is the conventionally cleaned radiance number. Okay, and the black bars are the number of cloud-free observations. Each of these vertical lines is July. Okay, so now we know that the monsoon in Bombay peaks every July. There are fewer cloud-free months in July, in August. In June here, there are fewer cloud-free months. There's more in July, okay, and so on. And for example, this is July, August, September. Here, September is a perfectly nice month. But here, September is a month with 0 observations. Okay, so this is what the raw data looks like when we do conventional cleaning. If we analyze the radiance after conventional cleaning added up across the 96 homogeneous regions of India, we find a powerful seasonality. For example, consider July. July is the peak month of the monsoon. This is the kernel density plot of the July seasonal factor. And you see that the modal value of the seasonal factor is a bit below 30%. So there's a pretty big reduction in the radiance every July. As I said, this is the kernel density plot of the July seasonal factor, the percentage deviation in July away from the annual mean. And so this is large scale evidence across the 96 HRs spread all over India. It's not 1 pixel in Bombay. What might be going on? We could think of 2 rival explanations. Either you think that there is seasonality in economic activity. Maybe in July there is less economic activity in India. Or maybe there is a physical problem. Maybe there is signal attenuation. So our intuition runs like this. Suppose there are 5 images in June. Okay, so out of 30 days in June, there are only 5 days on which there are cloud-free images as chosen by NASA and NOAA. Could it be that even on those 5 days, so because 5 is a small number, it's a cloudy month, could it be that even on those 5 days, there are actually light clouds which are attenuating the signal? So that way there is a bias whenever the number of cloud-free images is low. Now, straight away from the existing nighttime lights literature, there is a problem for explanation A, which is that nighttime lights do not respond in a short-term way to fluctuations in economic outcomes. So for example, when you get an event like the Asian crisis, the Asian financial crisis, there is no large adverse impact on nighttime lights immediately. The nighttime lights are street lights and lighting of commercial structures, and these things don't respond immediately. So even if there was a seasonal effect, it would be hard to generate a 20%, 30% decline in July. This is where we bring in the ground truth. Using the CMI CPHS data, we are able to get the monthly time series in the homogeneous region that is called Bombay. Okay, the black line shows you the seasonality of income in Bombay. And so you see there are small seasonal effects in Bombay. So there is about 4% lower output in May in Bombay. But the red line is the seasonality of the night lights. And this is just completely out of line. Okay, so this is saying that there is about 28% lower output in July. And there is nothing remotely like that in income. So this encourages us to think that there's something going wrong here. It just doesn't make sense that there is no great seasonality in income. Bombay is a services city. There is no seasonal fluctuation in the income in Bombay. And there is a huge seasonal component in the fluctuations of night lights. We scale this up on an all India level. So we look at all the 96 HRs. And we focus on a number that we call the seasonal factor range. This is the difference between the most positive seasonal factor and the lowest seasonal factor. So the gap between the two is what we call seasonal factor range. And what you see in the black line, this is the seasonality of income, is that there is a mode at about 10%, okay, 8%, 9%, 10%. So there is seasonality in income in India, but it's a modest magnitude. It's about 8, 9, 10% is the seasonal factor range. but the mode with the nighttime lights data is about 55 or 60%. This is out of line. So there's a very big seasonal component. These are kernel plots across 96 homogeneous regions of India. And there is a seasonal component in the night lights data, which is just not there in the income. Some people are just doing seasonal adjustment when faced with the night lights data. And we think that's unsatisfying because there is a seasonality in income. And I showed you earlier, sometimes there's a September that's a cloudy month. Sometimes there's a December that's a cloudy month. These are not seasonal patterns. This is bias. And so we should look for methods to measure and remove this bias so that we clean the data. We let the true seasonality of the nighttime lights data emerge in the data rather than just pretending that the seasonality doesn't exist. We find it useful to categorize all the pixels into 4 categories. Okay, so case 1 is a pixel with low radiance. If the radiance values are low, then whether there are clouds or not is not going to matter a lot. And in any case, these pixels are removed in the conventional cleaning. They are not the lit pixels. So case A is not important. Case B is a pixel where really it's sunny all the time. Most months are highly sunny, so there is no big bias problem. So there is a low bias and it's not a big problem. There is no problem there to solve. Case C is a difficult kind of pixel where it's mostly cloudy all through the year. In that case, it's not easy to identify the bias and it's not easy to design a bias correction scheme. In this paper, we do not solve the case C pixels. And finally, there are case D pixels. These are nice pixels like what I just showed you for 1 pixel in Bombay, where some months are sunny and some months are cloudy. And we are able to estimate and correct for the bias. So in this paper, we really solve the case D. Case A is removed because of conventional cleaning. Case B is not a problem. We do not solve case C. Here's 1 pixel in Bombay, which again, the same pixel that we showed earlier, and we call this a case D pixel. On the y-axis, we remove the time trend from log radiance, and on the x-axis, we put the number of cloud-free observations. Okay, so and you see the radiance is higher for the months where there are more cloud-free days. Okay, and then there is a cluster of observations here where the radiance is lower and there is a small number of cloud-free observations. Okay, and it's just not reasonable that there should be some correlation between GDP and the number of cloud-free days in a city like Bombay, which is really all about services. So we're able to fit a LOS into this data, and this straight away suggests a bias correction scheme that this is the kind of value that should normally obtain. And when you see a pixel about here, you take this vertical distance and you add it back into the pixel. Okay, so that's the bias correction scheme in a nutshell. There are many complications that have to be done to make it more robust. I refer you to the paper, but this is roughly what is going on. That when you see a pattern like this, A, there is bias, and B, there is a ready design of a bias correction scheme. So this is what we do as our bias correction scheme. For each pixel, we estimate the LOS. We measure the bias using this and we add it back. But there are many elements in the algorithm where our approach is we want to be extremely conservative. We just don't just run this for all the 16 million pixels. There are many steps in the algorithm where we check and we check and we check and we become absolutely sure that there is a bias and that this is a class D pixel and the bias is identified, and we can safely add back the bias into the month. So we only modify data for a pixel when we are sure. When there is the slightest doubt, we leave the raw data untouched. Okay, so our algorithm starts at the raw NASA NOAA data that has been conventionally cleaned, and it implements this kind of bias correction cautiously. For many pixels, we do absolutely nothing. Even in the pixels where bias correction is done, it is applied to certain months. Most months are left intact. We're extremely cautious. I refer you to the paper to see all the steps of care that are taken in order to be safe when doing this. Here's an example. There's a case D city, Bombay, where there are good months and there are cloudy months. There are bright months and there are cloudy months. The red line is conventionally cleaned radiance data, and the blue line is our bias corrected data. So you see that the extreme peaks where the red line seems to collapse every year in the monsoon, this is significantly but not entirely diminished. Let's look at the seasonal factors for Bombay. The black line is the seasonality in income, and I already showed this to you earlier. There is a small decline in output in Bombay in May. Apart from that, there is not a lot of seasonality in income in Bombay. The blue line is the seasonality in our bias corrected data, and we are close to the black line, but we are not perfect. Okay? You could say we are being too cautious and we don't remove the bias completely, but we definitely come much closer to the seasonality of the black line. The purple line is the seasonality in the World Bank data, which is what most researchers have been using so far. And the red line is the seasonality in the conventionally cleaned data. So we think we're making significant progress. We think it's Pareto superior to use our bias corrected data compared to either the World Bank's data or the conventionally cleaned data. Here's an example of a case B city. Dubai is a place where it's sunny all the time. So our careful, cautious algorithm does not make any big difference. There are a couple of months where there are some clouds and we fix it up. It makes a small difference. It's reassuring to see that the method works correctly when faced with a case B city. So there is no great problem of clouds coming in the way with Dubai, and our method delivers sensible results. Here's an interesting class C city, and that is Singapore. In the paper, we show the detailed evidence. Singapore is cloudy all the time. There are very few bright months in Singapore. And so as a consequence, the magnitude of the correction that we do through our bias correction algorithm is relatively modest. We do generate a certain amount of gain, but we think of this as an incomplete bias correction. So in the case of Dubai, we think that the radiance data is truly depicting what is the radiance in Dubai. In the case of Singapore, we think our bias corrected data still contains some bias, and the true radiance of Singapore is even higher than this. So we apply this method to all the homogeneous regions of India, and we aggregate up the entire radiance of India. The red line is the conventionally cleaned aggregate radiance for India, and the blue line is our bias corrected data. So once again, you see that by adding in the bias, we get systematically higher values, and these extreme intra-year fluctuations, which are associated with clouds, are significantly but not completely removed. Here's the time series of our bias corrected data. This is the upper blue line, juxtaposed against the aggregate income as seen in the CMI consumer pyramids dataset. So in the CMI CPHS, there is a relative stagnation of the aggregate income till about 2016. Then there's a period of GDP growth, and then there is a period of stagnation again. Our nighttime radiance data does show some increases of output through that period, and then the stagnation towards the end. It's puzzling that the World Bank data has the seasonal dips. It also does not have the systematic growth of radiance that should be seen in a period of 6 years where there has been a significant amount of GDP growth in India. Here are the 4 seasonal patterns. The black line is the seasonality of the aggregate income of India. Okay? There is seasonality of income in India, and that is picked up in the black line. Our bias corrected data is the blue line, and it is close to the black line, but it's not perfect. We have not eliminated the spurious seasonality in this data. And the bottom 2 seasonal patterns, the seasonal factors, are the World Bank data and the conventionally clean data, both of which have a lot of seasonality that is out of line with the black line. That's the seasonality of the income. So we come closer to the seasonality of income, but we are not entirely there. So this has some nice downstream implications. We have released a open source Julia package that does both the conventional cleaning and the new bias correction scheme. This consumes a VIIRS dataset at the input and makes a bias corrected dataset. So this can be used by researchers in remote sensing to further develop and augment these methods, and by researchers in applied economics who get a better dataset. As I said, we're not perfect, we're conservative. We modify radiance values only when we're quite confident this will help. We think the bias corrected data is Pareto superior compared to the conventionally cleaned data. And so all users of economic measurement using nighttime lights data will benefit from this work. So my co-authors and I are very happy to talk with you further and engage with you in this work. Thank you.